Okay, good afternoon. I hope you can hear me. So let's start today's lecture by recalling what we did last time, right? So we had a field K and a valuation on that field, which we called V. Now this valuation was supposed to be discrete and of course not trivial. Huh? And we assumed that the field is complete for this valuation, which amounts to saying that the ring OV is the completion. It's a projective limit of this OV modulo PV to the N. I hope you recall the notation. OV is the set of X in K such that V of X is positive and PV is the set of elements of K or OV, whatever, OV, such that V of X is strictly positive. And the residue field is denoted little kV. It's defined to be OV modulo PV. So last time what we had proved, these are the hypotheses. Our field K comes with a valuation which is discrete and it is complete for that discrete valuation. And we choose an algebraic closure, K bar, of this field K. Then last time what we proved is that there's a unique valuation V bar on K bar whose restriction to K is the given valuation V, right? There's a unique valuation on the algebraic closure whose restriction to K is the given valuation V. This is what we had proved. Actually, we had proved a little more. And among those things was the fact that if I have a finite extension L of K, a finite extension, then the valuation, the extension of the valuation V to the valuation W on L, the same thing as the restriction of V bar to L is actually a discrete valuation. V is discrete by hypothesis. W, we said that there's a unique extension of V to W, but now I'm saying that this W is also discrete. And the ring OW is the inverse limit of, so the ring OW is defined similarly. It's the OW is the set of X in L such that W of X is positive and so on, right? So this ring OW is the inverse limit of, and PW is defined similarly, the same condition, except that the valuation is required to be strictly positive. Okay, and there was this formula for the valuation W at each finite stage. L over K is finite. I have my valuation V here and the extension W to L. Then W is actually given by this explicit formula. You take an X in L, take its norm down to K, take the valuation of that norm and divide by the degree of L over K. Okay? And another thing which we proved is that the ring OW, which is defined in terms of the valuation W, is actually also equal to the integral closure of OV in L. So we could have proceeded this way. We have valuation V on K, and then we have this valuation ring OV. I take a finite extension L. Either I extend V to valuation W on L and define the ring OW, or I can directly define OW as the integral closure of OV in OW, right? In L, the integral closure of OV in L. Okay. So here is something which I might have stated last time. If I have two elements of K bar, which are K conjugate, which of course means that there is a K automorphism from K bar to K, right? K automorphism means that the restriction to K is the identity map of K. If I have such an automorphism of the field K bar, then they are called conjugates. X and X prime are called K conjugates if there is such an automorphism which takes X to X prime. Sigma of X is equal to X prime. I'm just recalling the definition of two elements of K bar being conjugate over K. And the proposition says that if they are conjugate over K, then they have the same valuation V bar. V bar of X is the same as V bar of X prime. Okay, let's prove this. So take a K automorphism sigma of the field K bar, which takes X such that sigma of X is not, I don't want to write sigma of X prime, I want to write sigma of X is equal to X prime, right? That's what it means for X and X prime to be K conjugate. Then what I have is a valuation W on K bar, not W, was it V bar? I have a valuation V bar. So it's a valuation with values in R union plus infinity. And I have my sigma, which is here. So I can take this composite. This is called V sigma, right? That is also a valuation on K bar. There's nothing to verify really because sigma is an automorphism of the field K bar. And the restriction of this, I should have written the restriction of V bar composed with sigma. The restriction of this to K is also equal to the given valuation V. Now, by the uniqueness of the extension of V to K bar, this V bar is the unique extension of V as a valuation to K bar. We must have this V bar composed with sigma is equal to V bar. Because we have got two valuations now. This was V bar, this is also V bar. So we have got two extensions, V bar and what is it? V bar sigma. These are two extensions of V from K to K bar. But by uniqueness, they have to be equal. So then V bar of X prime is equal to V bar of sigma of X because that's what X prime is. X prime is sigma of X. So that is this, that can be written as V bar composed with sigma of X, but V bar composed with sigma is equal to V bar. I've made so many typos today. Huh? So it's good. You have an exercise, you have to keep track of the typo, the mistakes that I've made today. Maybe I didn't sleep well last night. Okay, let's continue. So you have to be attentive because you see I made some mistakes. It should be V bar here. And that's what we had to prove. Did we have, oh yeah, that's what we have to prove. Right? V bar of X is equal to V bar of X prime. And we have proved that V bar of X prime is equal to V bar of X. That's it. Okay, so here is the next proposition. That if I have two elements which are K conjugate, if they are conjugate over K, then the V bar of their difference is greater than the V bar of X minus alpha for any alpha in K. You see, the greater the valuation of something, closer it is to 0. You think of it this way. The bigger a number is, closer it is to plus infinity. So if you translate that in terms of valuations, what it means is the bigger the valuation of an element, the closer that element is to 0. So this sort of a thing says that X is closer to any of its conjugates, closer to any of its conjugates than to any element of the base field K. Of course, X and X prime are K conjugates. Then, okay, so let's prove this. I'll prove it by a contradiction. I have to prove this inequality, right? So let me assume the contrary inequality. So let me assume that V bar of X minus X prime is strictly less than V bar of X minus alpha. Then what happens? I can write V bar of X prime minus alpha as V bar of, I subtract X and add X. Then I got two terms, X prime minus X and X minus alpha. And what do I know? The valuation of this thing is smaller than the valuation of this thing by hypothesis. This is what I'm assuming, right? So when I have V of X plus Y is equal to V of X if V of X is strictly less than V of Y, right? And this is what is happening here. The valuation of this thing is strictly less than the valuation of this thing. So the valuation of the sum is this. And what is given to me? It's given to me that this is strictly less than, I mean, this is the hypothesis that it's strictly less than V bar of X minus alpha. So what have we got? V bar of X prime minus alpha is strictly less than V bar of X minus alpha. But that's not possible because X prime minus alpha and X minus alpha are K conjugates because X prime and X are K conjugates by hypothesis. So this contradiction proves that my assumption that there's this strict inequality, that there's this inequality in the other direction doesn't work, and therefore I have proved this inequality here. Okay, here is a very useful statement called Krsnalemma, and it says the following. So suppose that some element X of K bar is separable over my base field K. What it means is that all its conjugates are distinct. So its conjugates, let's call them X1, which is X itself. Then there's some other conjugate, X2, and so on, up to Xn, where of course n will have to be equal to the degree of, what is it, Kx over K. The degrees, this, right? So I have to prove that. What do I have to prove? I have not yet stated it. I'm just setting up notation. I have an element which is separable over K, and these are its conjugates. Fine. I'm saying that if V bar of Y minus X is strictly greater than V bar of X minus Xj, these Xj's are the conjugates of X other than X itself. Because conjugate 1, number 1 is X itself, and number 2 to n are the other conjugates of X. So if the valuation, if V bar of Y minus X for some Y in K bar is strictly greater than each of the V bars of X minus Xj for J going from 2 to n, then this Kx is actually contained in Ky. this is quite useful in showing that two subfields of K bar are actually equal. They define they are the same. So you get an inclusion like this, and maybe you already know that the degree of the degrees are the same or something, and therefore you will get equality. But let's go to the proof of this statement. So let's show that for every ky automorphism of K bar, right? I mean, what you have is K, and then you have Ky, and you have K bar, and I have my X in K bar having some property. I want to show that X is actually in Ky. How can I show such a thing? If I show that for every Ky automorphism, sigma from K bar to K bar, if I have sigma of X is equal to X, then what I can prove is that X belongs to the separable closure of Ky in K bar. But X is itself separable, right? I have this, and I know that this X is separable over Ky. Then, of course, this implies that X is actually in Ky. And this, of course, implies that Kx is contained in Ky. So this is the idea of the proof, and let's that's the strategy of the proof. So let's start with Ky automorphism sigma, such that sigma of X. No, we are not starting with that. This is what we have to show, that sigma of X is equal to X for every Ky automorphism sigma of K bar. What I know is that sigma of Y is equal to Y, because it's, of course, after all, a Ky automorphism. And I also know that sigma of X is equal to Xi for some I in 1 to n, because these are the only conjugates. These are all the conjugates of X. So sigma, being an automorphism of K bar, has to take X to some conjugate of X, and every conjugate is Xi for some I, right? Now, what I know is that because X and X prime are conjugate, V bar of Y minus X is equal to V bar of Y minus Xi. Also, V bar of Y minus X is strictly greater than V bar of Y minus Xj for J in 2 to n. Why do I have this? That is the hypothesis. That's this hypothesis here. V bar of Y minus X is strictly greater than V bar of X minus J for every J going from 2 to n. And therefore, if I have to have this, the only possibility is that I is equal to 1. And therefore, sigma of X is equal to X. Now, which means that X is left fixed by every automorphism, every Ky automorphism of K bar, and therefore X is in Ky. Okay, so that's the proof of Krsna's lemma. I don't know why this stupid thing is happening, but anyway. Okay.
So the statement, the before statement, you say that if X and X bar are conjugate,
Yes.
then V of X minus X bar greater than or equal to V of X minus alpha for all alpha belongs to K. So whether the converse will be true, so let X is fixed, and if there exists X prime belongs to K, such that V of X minus X prime greater than or equal to V of X minus alpha for any alpha belongs to K.
Okay.
Then whether X and X prime are conjugate?
Of course not. No, that's impossible, because you see, X can have only finitely many conjugates. And there are infinitely
Right.
many elements in K bar which will satisfy this kind of a. No, that's not likely to be true. Okay, no. This is not a characterization of conjugates of X by any means. Okay. So let's continue. So this Krsnalemma is, as I said, useful for showing that Kx is contained in Ky under suitable hypothesis, of course. So now I want to introduce this notion of the ramification index. I think Supriya had already done a little bit about it. I don't know whether she did it in this generality, but or in a special case. But here is the general setup. What is the setup? I have a field K, which is complete for a discrete valuation V. And I have the ring of integers OV. This OV is also sometimes called the ring of integers of K. When K is thought of as a valued field, valued means field with a fixed valuation. Then I have this ring of integers OV, and this is painful. And the unique maximal ideal PV of OV and the residue field KV, right? Then I have an extension L of K of degree N. And then I have this unique extension W of the valuation V to L. Okay? In this situation, so we have already remarked that this W is also discrete. V was discrete by hypothesis. That's what we are taking. Then we are constructing some W, and we had seen that this W is also, it's not only unique, but it's also discrete. And the ramification index of L over K is simply defined to be, this is the notation we will use, E W over V is the index of this subgroup. No, this is not the subgroup. This is the whole group. The index of this subgroup in this big group, right? So we have the triangle, I don't know where to draw it, but here goes L, which contains K, and here you have R union plus infinity. So this is V, and this is W. And if I take the invertible elements, then I can forget about this plus infinity. So I'll get subgroups of R, and they are discrete subgroups, and this V of K bar, K star is contained in W of L star, right? That's what. V of K star is contained in W of L star. And they are both discrete subgroups, so each of them is isomorphic to Z. So if I choose an isomorphism of this with Z, I know all subgroups of Z, right? Every subgroup of Z is of the form A times Z for a unique A, which is strictly positive. I can have, but okay. The subgroup is also isomorphic to Z, then it has to be strictly positive, right? Okay, so that unique A, that this index is called the index, right? So this index is called the ramification index of L over K. L over K, it has a certain degree, but now I'm defining the ramification index, which will sometimes be denoted EL over K, but for the time being, let's denote it by EW over L. So it is just the index of the subgroup V K star inside V W L star. So there are other ways of expressing the same thing. So since the valuation on K is discrete, it has a uniformizer. the uniformizer, recall that it's either a generator of PV or of a positive generator of Vk star. Vk star is isomorphic to Z. It has two generators. Not only is it isomorphic to Z, but it's a subgroup of R, the additive group, and therefore it has a unique positive generator. And any pi W, pi V, such that V of pi V is the positive generator of Vk star, is a uniformizer. So I'll not keep on recalling these things, right? I mean, you should you should learn the definitions, because if you keep on repeating, then it becomes impossible to make any progress. Okay, so if I take a uniformizer pi V of K, and then of course it's an element of OW as well, so it can, it will generate a certain principal ideal. In any case, all ideals, it will generate an ideal of OW, and all ideals of OW are powers of PW. And that exponent here is called the ramification index. Of course, you can check that this exponent is the same as this index here. A third way of thinking of the ramification index is you take this pi V, a uniformizer of OV, and you think of it as an element in OW, right? Every element of OW can be written as a unit times some power of a uniformizer. Pi W is a uniformizer of OW, right? Pi W is a uniformizer of OW. So every element of OW can be written as a unit times a suitable power of a uniformizer, and the exponent here is called the ramification index of L over K, or of W over V, right? Finally, there's a fourth way of thinking about it, which is that, I have my K star, which is contained in L star here, and then I have the map from K star to the quotient modulo the units, right? K star modulo OV star. Here also I have this quotient of L star modulo OW star, and therefore there's this induced map, which can be seen to be an inclusion, because OV star is just OW star intersected with K star. And this group is isomorphic to Z, this group is isomorphic to Z. So here is a subgroup of this group which is isomorphic to Z, and the index is called the ramification index, and denoted E of W over V. So the first observation is that this ramification index divides the degree of L over K. Why is that? Because n times W L star is contained in V K star. Why is that? Because this W of something, whatever, was defined as V of the norm of that thing. Here, if you have X here, then W of X is V times the norm of X divided by the degree, N. So if I multiply by N on both sides, then I'll get N times W of whatever is V of something. So N times W of L star is contained in V of K star. And therefore, this ramification index divides this N. Another thing about basic elementary observation about the ramification index is that it's multiplicative, which means that if I have an extension L over K, the kind which I've been considering, and then I have a similar extension M over L of degree M, let's say, here it was degree N, then of course I'll have the degree of M over K is the product Mn, right? But not only is the degree multiplicative, I mean, this you should be familiar with this. Not only is the degree multiplicative, but so is the ramification index. The ramification index of m over k is the product of the ramification index of m over L times the ramification index of L over k. Okay. So this is, what's it? I mean, it's completely trivial, because if I have three groups, if I have A contains B, which contains C, where this is isomorphic to Z, and this is also isomorphic to Z, and this is also isomorphic to Z, and I have some index A here and the index B here and an index B here, then of course this index is A times B. I mean, that's all that is being said. Okay, so apart from this ramification index, there is another invariant of the extension L over K called the residual degree. So here is how it is defined. First, notice that PV is just the intersection of OV with PW, right? Because PV is the one for which the V should be strictly positive. And here, it means PW is the ones where W is strictly positive. And so, and W restricted to K is B. So that's what gives you this equality. These three things, this, and this. Okay, so now let's look at this inclusion of OV in OW. Here I go modulo OPW, OW modulo PW. And then what happens to PV in this quotient? PV goes to 0. And here, so this is OV modulo PV, right? So there has to be a unique map here like this, which makes this diagram commute. A unique homomorphism making this square commute. So by definition, the residual degree of L over K, which is denoted F of W over V, is equal to the degree of this extension. This is an extension of fields. KW over KV is an extension of fields. The degree of KW over KV is called the residual degree of L over K. Okay. And again, you have this multiplicativity as for the ramification multiplicativity. As for the ramification indices, you have, if you have a finite extension L of K and a finite extension M of L, and if V is the valuation here, W is the unique extension of V to L, and U is the unique extension of V to M, of course, then it has to be the unique extension of W to M as well, right? By uniqueness. Then you will have three ramification indices. What am I talking about? Residual degrees, not ramification indices. So you'll have three residual degrees. You'll have the residual degree here, the residual degree here, and the residual degree here. And the point is that you have this kind of multiplicativity. Just as the degree is multiplicative, so is the residual degree. But it was obvious that EW over V is finite. That was obvious. But the question is whether F is also finite. It's not obvious from the definition. This was obvious. So here is the proposition which reassures you about this finiteness. So the hypothesis is that I have a field which is complete for a discrete valuation, and L is a finite extension, W is the unique extension of V to L. then the residual degree is finite, and actually it's less than the degree of the extension. It's less than the degree of L over K. So let's just abbreviate this degree by n. And let's take n plus 1 elements in OW. What is this? Why am I taking all these n plus 1 elements? Anyway, so let us take, because the proof is saying so, let's take these n plus 1 elements here. And it says that they are k linearly dependent. That is, of course, obvious, because by hypothesis, the degree of L over K is n, and if I have n plus 1 elements, they have to be k linearly dependent. Okay, so there'll be these AIs, not all 0, right? That's what it means for them to be k linearly dependent. So there are these AIs, scalars AI, not all 0, which satisfy this equation of linear dependence. A1x1 plus A2x2 and so on, all the way up to AN plus 1, XN plus 1 is, this sum is equal to 0. Now these AIs are in the field K. If I multiply them all by the same power of pi v, pi v is of course a uniformizer of K. And the important thing is that K is equal to, what is it? OV, and I just need to invert pi v. So I can by just multiplying by a suitable power of pi v, I can clear denominators. That is what is being, this is called clearing the denominators. So AIs are no longer, they don't have anything in the denominator, they are these integers. And integers in this context means elements of OV. And I should be slightly clever and not take alpha too big, in order to ensure that one AJ is actually a unit. So this is easy. I mean, you know this. You just take alpha, you take alpha to be just right, so that you clear the denominators, and one of the alpha j's is actually a unit. Now you go modulo PV in this, so you get this relation, right? This relation now, all these coefficients are in OV, and one of them is a unit. So when I go modulo PV, all of them, they're these n plus 1. So what will I get? I'll get a relation like this: A1 bar, x1 bar, plus A2 bar, x2 bar, plus an plus 1 bar, xn plus 1 bar is equal to 0. So what this is saying is that any family of n plus 1 elements in, what is it? The residual field of L is KK linearly dependent. Because here is a relation of linear dependence. You know, these coefficients are, some of them might be 0, but not all of them are 0, because at least one of them is a unit, or rather the reduction of a unit. So the reduction of a unit is never 0. And what have I proved? I have proved that any family of n plus 1 elements of KL, you might say that no, these are not all, I mean, all possibilities. Of course, they are all possibilities, because I just take any n plus 1 elements in KL, I lift them to n plus 1 elements in OL, and then I apply this business OL. OL, as I said, sometimes I'll use the notation OL for OW. I've been calling it OW. So I lift them to OW, then I apply this business, and I'll get a linear relation of linear dependence with coefficients in KK. There is KOC. Again, I have called them KL and KK, whereas I said at the beginning that I'll call them KW and KV. So these notations are interchangeable. Later, we will use V and W less and less, and we'll use KL and KW and OK and OL and so on. That's because you don't need to then use these letters, V and W, all the time. Okay, so the next proposition is that the degree of L over K is equal to the product of EW over V and FW over V. This, remember, is the ramification index. And this is the residual degree. So the degree, and this is the degree of L over K, right? So the degree of a finite extension is equal to the product of the ramification index and the residual degree. Of course, one is talking about the degree of field K, I mean a finite extension of K, and where K itself is complete for a discrete valuation. Otherwise, these ramification index and residual degree, etc., might not even make sense, especially the ramification index. So that's one thing. And the other part of the proposition says that this OV module OW is actually free of the same rank as the degree of the extension. Okay, so this is going to be a slightly long proof. So I'll wait for a few minutes at this point to see if you have any questions. So if there are no questions, I'll continue. Now I have to prove that the first thing I have to prove is that the degree is the product of the ramification index and the residual degree. So let's just abbreviate the ramification index by E and the residual degree by F, without the decoration here and here. So what do we have? We have V of K star is E times W of L star. That's by the definition of the ramification index E. And I take a uniformizer pi W of L and I look at all its powers